follow and subscribe the channel for more interesting study topics. Hello students, how are you? Hope you are doing fine and preparing well for your final exams. So today we are discussing this chapter to understand the physics of sight. Our senses are they are our window to the world, aren't they? And you could argue that sight is the most powerful of them all. I mean, it lets us see everything from the words on the screen to galaxies millions of light years away. But have you ever really stopped to think about how it actually works? Seriously? Think about it for a second. Right now, information is just zipping from the screen through the air and somehow ending up inside your brain. So, what is that information? And how on earth does your body just snatch it out of thin air? So, the star of the show, of course, is the human eye. It is an absolutely incredible piece of biological engineering. But here's this thing. It's only half the story. Without its crucial partner, the eye is completely, utterly useless. To see anything, literally anything, our eyes need light. See, either an object makes its own light, like sun or stars, and this is how we see pretty much everything else. Light from a source bounces off an object and then enters your eyes. That bounce, that is the real secret to vision. So let's dive into that bounce. Because to really get a handle on sight, we have to understand the physics of reflection. And it turns out light is an absolute stickler for the rules. Okay, let's break this down. A beam of light, we'll call that our incident ray, comes in and strikes a mirror. It then bounces off in another direction, and that's our reflected ray. Now the first law of reflection is so simple, but it's profound. The angle it comes in at is always identical to the angle it leaves in. Means the angle of incident, which is denoted by I, and the angle of reflection denoted by angle R, they are always equal. And if we want to get really precise, physicists use this imaginary line that is perpendicular to the surface, and they call it the normal. So the angle between the incoming ray, the normal, that's the angle of incidence, and the angle between the outgoing ray or the reflected ray and the normal is called the angle of reflection. And here's the golden rule, the one that never ever changes. The angle of the incidence always equals the angle of reflection. No exception. Right? Now for the second law, which is just as crucial. The incoming ray, the normal line, and the outgoing ray, all three of them have to lie on the exact same plane or the flat surface, or we can just call it a plane. Just imagine it like a perfect two-dimensional game of cosmic pool being played out on a single flat sheet of paper. And this is where it gets really cool. If you bend that sheet of paper, if you bend that plane, the reflected ray seems to just disappear. But it's still there. The light is still perfectly obeying the first rule. But because it is bounced onto a totally different plane, you can't just see it from where you were looking before. Okay, so if these laws are totally set in stone, then why can you see your reflection in a polished mirror but not in, just say, a piece of cardboard? I mean, they are both reflecting lights. So what gives? Well, it all comes down to texture. A mirror is super smooth, so it reflects parallel rays of light in a really uniform, orderly way, which creates a clear image. We call this a regular reflection. Cardboard, on the other hand, is rough and chaotic. Its surface scatters the light in every direction imaginable, and that is what we call diffuse reflection, means scattered reflection. You can really see the difference here. Regular reflection is like that disciplined little army of light rays all marching in perfect formation, means they are reflected in a parallel way. Diffuse reflection, that's more like a chaotic mob where every single ray is just going its own way. But here's the absolute key takeaway. Diffuse reflection doesn't break the rules at all. For every single one of those scattered rays, the angle of incidence is still equal to the angle of reflection. The chaos isn't because of the physics is failing, but it's because the surface itself is chaotic. Means the surface is not regular or surface is uneven on a microscopic level. Okay, so we have got the rules down. Now let's have some fun with it. What happens when reflected light gets reflected again? Oh, you have definitely experienced this. You are at the hairdresser and they hold up a mirror behind you so you can see the back of your head in the mirror in front of you. What's happening? Well, the light from the back of your head, hits the rear mirror, bounce to the front mirror, and then bounce again right into your eyes. It's a double reflection. Now this is where things get really trippy. If you place two mirrors at a perfect right angle and put something between them, you don't get two reflections. No, you get three reflections, one from each mirror, and then this mysterious third image that is created by the light bouncing between them. And the principle is actually pretty simple. The smaller you make that angle between the mirrors, the more time the light can bounce back and forth between its escapes. And what does that mean? It means you get more and more and more images, means multiple images. So what's the logical conclusion here? If you make two mirrors perfectly parallel, you get that mind-bending infinite corridor of reflections you have probably seen in an elevator or a fitting room. It just seems to go on forever. And this whole idea of multiple reflections, that is exactly how a kaleidoscope works. Inside that little tube, there are two or more mirrors set at an angle. All those little colored pieces of glasses at the end get reflected over and over again, creating these beautiful complex patterns that are pretty much never the same twice. Now, all this talk about mirrors and light rays might seem like we have gone off on a tangent, but I promise we haven't. Now that we have mastered how light behaves out in the world, we can finally go back and solve our original mystery, the human eye. Okay, so let's trace the final most important part of light's big journey, from the outside world into the inner working of the eye, where all that light is finally transformed into what we call sight. Alright, here we go. First, light passes through the cornea, which is kind of like the eye's transparent front window. It then travels through the pupil, that black dot right in the middle. The iris, the colored part, acts like a muscle, making the pupil bigger or smaller to control just how much light gets in. Next up, a flexible lens focuses all those light rays, bending them perfectly onto the retina at the very back of the eye. You think of retina as a biological movie screen, and once the image is on that screen, the optic nerve picks up the show and sends it straight to the brain for processing. And that retina screen is just incredible. It's packed with millions of light sensitive cells, and there are two main types. You have got rods, which are our low light specialists for seeing in black and white, and then you have got cones, which gives us that rich, vibrant world of color when the lights are bright. And to finish, here is one last absolutely mind-bending twist for you. The lens in your eye, just like a simple camera lens, actually projects an upside down image into your retina. Upside down means an inverted image. That's right. Every single thing you have ever seen was first painted as an inverted picture on the back of your eyeball. So what incredible biological computer is powerful enough to constantly be flipping your entire world right side up? Well, that's a story for another time. Hope you had fun enjoying this lesson. Thank you. See you in the next video. Do follow and subscribe the channel for more interesting study topics.